Okay, in section 1.3 here, we're going to look a little bit more at functions and their graphs. We're going to look at intervals on which a function is increasing, decreasing, or constant. Use the graphs to locate relative maximums and minimums, and identify whether the functions are even or odd, and using their symmetry also to decide if the function is even or odd. Okay, so, increasing, decreasing, and constant functions. We say that a function is increasing on some open interval if f of x1, meaning the value of the function for x1, is less than the value of the function for x2 whenever x1 is less than x2. So we can kind of see here in the diagram, we've got this function, this graph here in blue, and we've got a value for x1 and a value for x2 down here. And notice that the corresponding function value for x1 and for x2, the value of f of x1 is below f of x2, which means as the x's are going out towards infinity, the value of the function is going up. And that indicates that as the x's are getting larger, the value of the function is increasing. We've got this kind of this upward slope, this upward direction to our graph. So for some x1 which is less than x2 on our interval I, whatever that interval might be, the value of the function at x1 is less than the value of the function at x2, meaning as the x's are increasing, the value of the function is also increasing. Now if we flip that around and look at a function that's decreasing, then that means as I start to move out the x-axis, as my x values are getting larger, the value of my function is actually going to be going down, and that indicates that the function is decreasing. It's kind of this downward hill on our function here. Okay? So that as for x1 being less than x2, as my x's are getting larger, the value of the function for those x's is actually going down. So the f of x1 would have a larger value than the function does at x2, indicating that the y values, the function values, are decreasing over some interval of x. And when we talk about a constant function, that just means that no matter how far the x's are going, the value of the function remains constant. It stays the same. So the indicator for a constant function is when we have this horizontal line. Okay? So a horizontal line indicates that the function is constant over some given interval. So if we look at the function here, f of x equals negative x cubed plus 3x squared. Okay? And it's a little difficult to try to get the graph to line up on the grid here, but 0, 0 is a point, and 3, 0 is a point, and then up here at the top we've got the point 2, 4. Okay? So what we want to look at is we want to identify any intervals, okay, over what values of x is the function increasing, decreasing, or constant. Okay? So increasing. Where does the graph appear to be going in an upward direction? Well, from here to here, we can see that the graph is moving up. So, on the interval from 0 to 2 on the x-axis, as x's move from 0 to 2, the function values, the y values, are increasing. They're going up. Okay? So our intervals here, the intervals are always going to be x values. And we're considering over what x values is the function increasing, over what x values is the function decreasing, and so on. Okay? So where is the function decreasing? Well, the function appears to be decreasing. The function is going in a downward direction, okay? And it changes down here at 0. So from negative infinity up to 0, the function is decreasing. As well as, if we look over here, from here on, the function is going down as well. So from 2 to positive infinity, as long as the x's are 2 or greater, the value of the function is going down. The function is decreasing. Okay. Is there anywhere that the function appears to be constant? Are there any horizontals? And the answer to that is no. Okay, so we're increasing on one interval and we're decreasing over the other two. Okay, here's another function. Here's a piece function. Okay, and again, same deal. We want to look at where is the function increasing, decreasing, or constant. Okay. Well, if we look at increasing, the only place that the graph appears to be going up is when x is 0 to infinity. As my x's are getting bigger than 0, notice that the graph is going in an upward direction. So my function is increasing from 0 to infinity. Decreasing, there is nowhere that this function is decreasing. But we do have an area here where the function is constant, where we have a horizontal line. Okay? So our constant is going to be from negative infinity up to 0 on the x-axis. Okay? Remember, again, that these are x values in our interval. As the x's are going from negative infinity up to 0, the y values are remaining constant. As the x values are going from 0 up to infinity, the function's value, the y values, are going up. They're increasing. Okay? So our function is increasing from 0 to infinity along the x-axis, and it is constant from negative infinity to 0. Okay. Maximums and minimums. We remember doing this, hopefully, from Algebra 2, where we talked about maxes and mins. Okay. Kind of a fancy definition here. We say that f of a is a relative maximum of the function f if there is some open interval that contains a where f of a is greater than f of x. Okay? So what we're kind of talking about there is that we've got some graph. Okay? Let's just put this graph here. And we've got some open interval. Okay, we'll make those in red. Okay, there's some interval in here. And somewhere in here there is a value a. Okay. So we've got our open interval I going from here to here. Okay. And somewhere in there is some value a. And up top here we would have the point a f of a. Okay, the function's value at a. So this would come over here. That's f of a. And what we're saying is that no matter what other values I may pick within this interval I, let's call this x1, okay, then over here I'd have f of x1. And notice that f of a is greater than f of x1. It's farther up the y-axis. And if I pick some other value over here, call it x2, okay, that comes over here. Again, somewhere in here, we've got another value, f of x2, that the same thing happens. F of a is still farther up the y-axis than f of x2. That indicates that f of a is a relative maximum. Okay? So there is a relative max at x equals a, and the value is f of a, whatever that value of that function is, whatever that y-coordinate, that's the value of the maximum. Now we have the same kind of thought process for minimums, only instead of having a value that's larger, we have a value that's smaller. And we had a little bit of a typographical error here. This should be f of x. Okay. So what we should have here is that f of b is less than f of x for all x is not equal to b. Okay. That would indicate that we have a relative minimum. So if we kind of go with the same shape of graph here, okay, we'll piece out some open interval here, I. Okay. So there's our open interval I. All we're saying is that somewhere in here is this value of b. Okay. Which means as we come across, we'd have f of b right here. So if I picked any other values, okay, if I picked a value of x here, then notice that when I come over to the function, the y, that the f of x is higher. So I do indeed have that f of b is less than f of x, indicating that I have a relative minimum at that value of b. And the value of the minimum is whatever f of b is. So I have a minimum at some particular x value. What is the minimum value? That's the function value for that b. Okay? So we'll kind of, and maybe that'll clear it up a little bit. Okay, so here's a function for f of x equals sine x. We'll look at the sine graphs a lot more later on in the year. But the question is, says f has a relative maximum at x equals what? Well, what x value is there a high point on the graph? Well, that high point on the graph we can see is happening right here when x is equal to pi divided by 2. And the relative maximum is the function's value at pi over 2. So f of pi over 2, which is equal to 1. So that relative maximum has a value of 1. How about a relative minimum? Well, where is there a low spot on the graph? There's a low spot on the graph right here. So when x is 3 pi divided by 2, we've got a minimum. And that relative minimum, its value occurs at f of 3 pi over 2, and it's equal to -1. Okay? So we have a minimum or maximum occurring at some x value, and the value of that maximum or minimum is the function's value. Okay? So that has a minimum at x equals 3 pi over 2, and the value of that minimum, the actual minimum value, is the function's value for that particular x, which in this case the minimum is at -1. Okay, so here's another example. Here's a graph. Okay, where does f have a relative maximum? Well, so where along the x-axis do you notice that there is a high point at the graph? Well, when x equals 0, okay, when x is 0, here's my high point on the graph. There's my peak. Okay, what is the relative maximum? Well, the relative maximum would be the value of the function, which is 2, because f of 0 equals 2, and the 2 would be my relative maximum. Okay, where is there a relative minimum? Well, where is there a low point on the graph? Well, there's a low point right over here when x equals 3. And what is the relative minimum? Well, the relative minimum would be the value of f of 3, which turns out to be -3. Okay, and what are the zeros? Remember, we kind of mentioned and we talked about the zeros of a function occur at the x values where the graph crosses the x-axis. So the zeros of the function are at -1, +1, and 4. Okay, so those are the zeros. If I wanted the x-intercepts, that I would list out the ordered pair for the point along the x-axis. If I want the zeros, I'm just giving the x values of where that graph is going to cross the x-axis. Okay. All right, even and odd. Okay, even and odd functions can be determined by evaluating f of -x. Okay, so if I evaluate f of -x and I still get the original function f of x, I get the same thing back, then that tells me that that is an even function. And it will be symmetric with the y-axis, meaning if I folded the graph on the y-axis, all the points on the right and all the points on the left would match up when I fold it in half. Okay? If I evaluate f of -x and I get the opposite of what I started with, that indicates that the function is odd, and the symmetry is with the origin, meaning if I were to have the point 1, 1, then I would also have the point -1, -1. It's symmetric with the origin. I put in the opposite x, I get the opposite y. So if we look at these two examples, is the function even, odd, or neither? Well, to determine that, we're going to evaluate f of -x. So I'm going to replace x with -x, and a -x squared becomes +x squared plus 6. Well, what is x squared plus 6? That was the original f of x. So I have f of negative x equals f of x, and if those things are equal, that tells me that this is an even function. Okay? And I will have symmetry with the y-axis. Okay? It'll be like the graph is a mirror image in the y-axis. So let's look at part B, g of x. If I evaluate g of negative x, I have 7 times negative x cubed minus negative x, which gives me a negative 7x cubed plus x. But if I were to factor out the negative, it would be the opposite, or the negative, of 7x cubed minus x. And this graph right here, that's really g of x. So I really have the opposite of g of x. So g of negative x equals the opposite of g of x. Therefore, I have an odd function. Okay? So when I evaluate my function for the opposite of x, or negative x, when I throw in the opposite of x and simplify, if I end up with the same function I started with, that tells me it's even. If I end up with the opposite of what I started with, okay, I've got the opposite or the negative of g of x, then that tells me that the function is odd. Okay. How about h? Okay, see if you can do h of x. So maybe pause the video, try this one, and then look at the solution. Alright, so h of negative x would mean I would take negative x to the 5th plus 1. Well, a negative to an odd power stays negative. Okay. So I have a negative x to the 5th plus 1. And even if I factor out the negative, I still don't get back what I started with. Okay. So since I don't end up with h of x again, I don't end up with the opposite of h of x again, okay, I would say that this function is neither even nor odd. It doesn't fit either of those patterns. Okay? So functions can be even, they could be odd, or they could be neither. They may not fall into either one of those symmetric patterns. And that's the case here with h. Okay? Okay, so make sure you go over those notes. If you need to, go back and watch the video again. Come with questions over things you had confusion on. We'll try to clear those questions up at the beginning of class, and then we'll get started on working on the assignment. Okay, we'll see you then.